Heat, denoted by the variable Q, with units of joules, or BTU in the US customary unit system, is a form of energy that is transferred across a boundary given there exists a temperature difference between the system and surroundings. Now, heat always flows from a high to a low potential. That is, heat is going to flow from a high temperature reservoir to a colder temperature reservoir. A body or system does not contain heat. Heat is only identifiable as it crosses our control surface of our system. Once two systems are in thermal equilibrium, i.e. there's no potential to drive the flow of heat, heat transfer ceases. Now, unlike work, if we transfer heat into a system, it is a positive quantity. And if we transfer heat out of a system, it is a negative quantity. This is opposite of our definition of work. If there is no heat transference between our surroundings and our system, Q is equal to 0, and this is referred to as an adiabatic process. Heat is also path dependent, and our heat supplied going from state 1 to state 2 is equal to the integral from state 1 to 2 of delta Q. Now, the rate at which heat is transferred is a time rate dependent term, Q dot, which is delta Q per T, and this has units of joules per second or watts. And we can also have heat on a per unit mass basis. Our specific heat, not to be confused with the specific heat, i.e. the material property, defining how much heat has to be supplied to raise 1 unit mass, 1 unit degree, is our capital Q per M. Now, oftentimes, we are either given Q or we are solving for Q. We have no other formulation to represent this variable. Until we take heat and mass transfer, we have no other way of determining Q. Let us look at example 2. Consider a piston cylinder device that contains air. The piston has a mass of 45 kilograms and an area of 900 centimeters squared. Heat is applied to the assembly such that the volume increases by 45,000 cubic centimeters. If the mass of the air in the system is 0.27 kilograms and our internal energy is increased by 42 kilojoule per kg, we want to determine the amount of heat transferred during this process. For us to begin, we are going to start with our conservation of energy equation. dE is equal to du plus dke plus dpe, which is equal to our heat supplied less our work done. Since there are no changes of kinetic or potential energy, we say our heat supplied is equal to our work done on our system plus the change of our internal energy. Thus, we need to determine du and our work done by the system. Our work from state 1 to state 2 is equal to the integral from state 1 to 2 of PdV. Since this is a piston cylinder setup, we're assuming our pressure is going to remain constant during our expansion process. So we'd have P times the change of volume between our final and our initial state. To determine the pressure within our piston, we must employ a force balance. The pressure within this piston must support the mass of our piston accelerated by gravity. That is, our pressure within our system is going to be our applied force per our area. Our force is equal to the mass of the piston, 45 kilograms, times the gravitational acceleration, 9.81 meters per second squared, per the area of our piston, 0.09 meters squared. Or the pressure within this device is 4.905 kPa. Thus, if we evaluate our work term, our work going from state 1 to state 2 is our pressure times the change of our volume, 4.905 kPa times 0.045 meters cubed. Or we're producing 0.22 kilojoules of work. Therefore, our heat added is simply our work plus the change of our internal energies. Our work was 0.22 kilojoules, and our change of our internal energy would be our mass times the change of our specific internal energy, which was given as 42 kilojoule per kg. So we'd have our mass of 0.27 kilograms times the change of our specific internal energy, 42 kilojoule per kg. And when we sum these two terms, our heat supplied has to be equal to 11.56 kilojoules.